Stackings of many similar objects are very common in natural scenes, but their high complexity makes them challenging to render in a real-time rasterization engine. Our pipeline is able to render stackings of up to millions of objects consistently among scales and in a fully dynamic setting, provided that, first, there is a low diversity of shapes, second, these shapes are spherical enough, and third, the stacking is dense enough. By spherical enough, we mean that the geometry of the grains, the stacked objects, is contained between an inner sphere and an outer sphere, and the closer the radii of these spheres, the better our performance is. Overall, closer grains are rendered using traditional mesh instances, and furthest grains are only points. So we focus on the seamless integration of an intermediate model that we base on impostors, and on the splitting process that distributes the grains among the three models. We try to leverage our hypothesis as much as possible in both of these components. So the pseudosphericity, for instance, is used in the splitting to do some early grain level occlusion culling prior to knowing the actual shapes of the grains, and then it is used again for the impostors by designing a sampling scheme that reduces the ghosting artifacts. And then the density. The density enables us to make the grain level culling statistical, even though it remains conservative, and is also important for the two-pass scheme that we use to draw the impostors. This scheme recycles the coarse depth buffer that was a byproduct of the grain level culling to first draw a batch of impostors that have a high probability of being fully visible, and only then renders the remaining impostors. This fosters the fragment level early Z-culling provided by the hardware and hence makes the rendering of impostors much more efficient. In the end, we're able to render even sound tracks with the ability to zoom on individual grains. To know more about the details of our pipeline, check out our paper on real-time multiscale rendering of dense dynamic stackings.